This is an overview of our senior Design2 project. For this, we did a Rubik's Cube solver. These are the members of the team. And for our overview, we'll give you an intro to the project, an overview of the design, and we'll show a video of our project functioning.
So the objective of this project was to develop and construct an automated system by April 20th to solve a Rubik's Cube for under $400. Our motivation was to demonstrate the IDA star search algorithm in a real-world application. Our project goals and deliverables were to have a 3D arm that can pick up and place a cube down within 5 seconds, a 3D arm that moves in 3 dimensions, an algorithm that can provide a Rubik's Cube solution in 60 seconds, a camera that completes scans in under 15 seconds, a prototype that can complete a 3x3 cube under 60 seconds, a mobile application to solve a delay time that is less than 1 second, and a low-side current sensing circuit monitor that monitors the servo performance in both the arm and the frame. This is an image of just our project implementation and our block diagram, and then the overview of design.
So for the Rubik's Cube solver, the final design of the Rubik's Cube solver is a robot that picks up a Rubik's Cube, solves it, and then places it into its original position and is initiated through an Android app.
For the discussion of our hardware design, the pick and place robot and solver robot move using servos that were programmed using Python and are powered from a SparkFun P-hat connected to the Raspberry Pi. The current sensing circuit uses the LM324 op-amp to amplify the voltage produced by the current of the load flowing through the shunt resistor. This voltage is then read through the ADC of the TIVA, which communicates with the Raspberry Pi via UART.
For the Android app design, we decided to keep it simple. All it's used for is to send and receive commands to the Raspberry Pi via an RFCOM server via Bluetooth. At the very beginning, the user will load in the app and will have an option to connect to the Raspberry Pi. Once that's initiated, you can then select to start a solve or select a pattern to choose from if you already have a solved Rubik's Cube. Once one of these options is selected, it'll send you to a diagnostic screen. Here, the Android app is simply receiving bytecodes from the Raspberry Pi, which tell it what phase of the solve it's at, and also displays the current that's being detected by the low side sensing curve.
For our master script running on the Raspberry Pi, it will first establish a Bluetooth connection with the mobile app. Then it will wait for the user to send a start command. This could be a bytecode for a normal solve or for a pattern, and it will operate differently depending. So for a already solved Rubik's Cube, it will run a pre-made script for that pattern and then move the finished cube back to the starting place. For a normal solve, it will scan the cube with our camera to identify each color of the square on every side. It will pass the data into Kosciemba's algorithm and get the solve moves. All of this done while sending bytecodes to the app so it knows the status of the solve. It will communicate those moves with the motor and then put the cube back.
For our methodology, we're using the V methodology model. This is an approach known for verification and validation. It is a sequential process in which the next phases begin only after the completion of the present phase. Steps don't move in a linear way, they are bent upwards. This V method proved to be the most intuitive and straightforward to implement. We based our design off the requirements outlined in the project goals and deliverables. Keeping these restraints in mind, we knew our device had to be both efficient and sturdy. We decided to use a push and turn gripper with 2 degrees of freedom after first testing this squeeze and turn grippers. Utilizing this idea allowed the construction of our project to become more compact, reduce the stress placed upon our servos. Our testing approach followed a trial and error type structure to configure cube and gripper positioning, as well as make sure the pick and place process goes smoothly.
For the discussion of results, the app runs without issues and correctly begins the process. Bluetooth connection between the Android phone and the Raspberry Pi is correctly established within 2 to 3 seconds, which aligns with our expectations. The pick and place arm quickly moves the cube around 3 seconds, and the computer vision code analyzes the colors on the cube, which allows for the algorithm to solve the cube puzzle. The IDA star algorithm solves the cube puzzle in an average of 18.5 moves, which allows the cube to be solved quickly. Unfortunately, our servo driver chip was compromised, so we could not execute the move set to solve the cube. The current sensing circuit is not yet added onto the robot to recurrent.
So these are the strengths and weaknesses of our projects. We have met expectations, unmet, and exceeded that are color-coded in the top. We wanted our 3D arm to pick up and place the cube within 5 seconds, but ours can actually do it in 3. Our arm did move in 3 degrees of freedom. It could provide a Rubik's Cube solution in 5 seconds instead of 60. The scan could be completed in 6 seconds. Our prototype could complete a 3x3 cube under 50 seconds. The mobile application delay time was almost negligible. The low side current sensing circuit was tested and functional on its own, but it was not integrated into the circuit quite yet. Future directions were to implement a 2x2 Rubik's Cube solver, improve the solving capabilities to make them faster, and expand the mobile application functionality.
In conclusion, our goal of developing and constructing an automated system by April 20th to solve a Rubik's Cube for under $400 was a partial success. Our automated system was able to meet or exceed expectations on 5.5 out of 7 requirements. Our failure was the inability to perform current analysis on all servos. Going forward, we would like to be able to complete an automated system that solves the 2x2, have faster solving capabilities, as well as expand the mobile application functionality.